And I hope this presentation title is right. Selective microscale sintering for next generation semiconductor bumps.
Mm-hmm.
You will most likely show us in a moment a
Yeah.
slightly different presentation title.
Yeah.
Very good. Michael, the stage is yours. Everything
All right.
works well.
Thank you. You can hear and see me?
Yes, perfect.
Good. Yeah. So I think, yeah, so thanks for having me here. So yeah, like you said, I'm Michael Cullinan. I'm from the University of Texas. I'm going to talk a little bit about our microscale selective layer sintering process that we use to make microscale metal 3D features, mostly for microelectronics sort of applications. Yeah, so yes, there you go. So yeah, so our main applications are in microelectronics, like I said. One of the things we're really concerned about is electronics packaging. So we've been working a lot on that sort of application. And one of the challenges there is, as we've been making finer and finer pitch features and going to 3D kind of stacked electronics sort of structures, the connections between the chip and the board or between chips need to get smaller and higher aspect ratio. And so typically those things are electroplated. They electroplate material into a hole, but as those get smaller and closer together, it becomes really hard to electroplate into deep, small holes. And so there's been a lot of interest in kind of going towards 3D printing for making a lot of these structures. So making things that are like, 10 micron diameter, 50 micron height, so 5:1 sort of aspect ratios at, small pitches. And so we started by looking at, what sorts of systems exist out there. And we need to do a few things. If we're doing semiconductor manufacturing, we need high volume, high print rates. So we need to, produce millimeters cubed per hour sort of print rates. We need to have 3D structures. We need to have micro scale resolutions, and we need to be able to print it in metals. And it turned out there weren't a whole lot of process that can do all of those things. So we started to develop kind of our new microscale selective, what we call microscale selective layer sintering process. And so if you're familiar with kind of the macro scale process, the way it works is basically you take a powder, metal powder, you spread it across a surface, then you use a laser to scan across that surface and melt the powder in certain areas to form a shape. Then you spread it on another layer of powder on top of that, repeat that process until you get a 3D structure, and then you can move your part out of your powder. And so when we go to the microscale, there's a few challenges with that. Typically, the powders we're talking about have featured, particle sizes of tens of microns in diameter. If we're trying to make, 1 micron part, we need, 100 nanometer or smaller sort of particle sizes. Typically, the laser beams are hundreds of microns in size. If we want to make micron scale parts, we need, micron scale lasers, and the heat spreads from these, and so those are some issues that we had. So we developed kind of a new system for how to do this. One of the kind of big change we made is, instead of having microscale particles in these systems, we have nanoscale particles. Problem with nanoscale particles is they tend to be sticky, and so if you have a bunch of nanoscale particles touching each other, they tend to agglomerate into much bigger things. And so we end up having to spread our nanoparticles as an ink as opposed to a powder. And so we spread kind of a micrometer, a few micrometers worth of ink onto a surface using like a slot die coating system. Try that out, bring it under our optical system. Bring it under our optical system here, where we can kind of expose it. Because we're trying to get micro scale features. That means, the spot size of the laser needs to be a micron or so. If we shrink the spot size from 100 microns to 1 micron, that scales our production rate by 10,000 times. And so to get around that, instead of just having one laser doing our scanning, we have a laser reflected through a micrometer array. So basically 4 million pixels at once. So within a 1 by 2 millimeter area, we'll have 2 million pixels in there that each is about a micron in size. And so we can bring back up our throughput back to kind of what we need for semiconductor manufacturing. And so we do that with, put our laser image onto our surface. We have a nano positioning stage there, so we can step around, kind of build a larger structure. Then we can go back to our coating system, lay down the next layer of nanoparticling, dry it out, sinter our particles together, and